Good afternoon. I'm giving this presentation on behalf of Lily Huan, who's currently residing in Taiwan and hopefully be back here in August to complete this work as part of her PhD. I also noticed this fell under the heading of charismatic marine predators, and I thought that might be a reflection of my past behaviour, but I wouldn't actually describe myself as charismatic. So I'm going to unashamedly use notes to progress through this talk. Beauty. It's fairly common knowledge that since the 1950s we've lost large portions of seagrass along the metropolitan coast, which equate to an area about the size of 50 square kilometres. To the blue economy, this represents probably an annual loss that equates to the millions, either in the commercial or the recreational fishing fraternity, or even just the movement of sand along the beaches and having to be replenished from lack of being trapped by the seagrass beds. Although the latest surveys have shown that we're actually having signs of recovery and that potentially that we are actually stabilising these seagrass beds. But one of the biggest challenges that we seem to find is actually trying to monitor this recovery and do it in a cost-effective method. In the past, we've relied quite heavily on aerial photographs, which have been quite haphazard, has been opportunistic, and in the recent days we've actually gone ahead and got quite high-level digital images. But the older ones are quite low in temporal resolution, so they're quite pixelated, and that has its own problems in trying to actually identify the different types of habitats. And as a consequence, often what we describe as seagrass was actually a reef, or what was a reef was actually became seagrass beds. And then even the most basic ability of just trying to actually define whether it's actually dead or alive. If a photograph's taken after a large storm, we may have large amounts of seagrass leaves moving around up and down the coast, and they represent what they think are seagrass beds when it's actually just seagrass leaves moving along. Mapping technology has certainly improved over the years, but we're still finding it quite difficult to actually classify, and it's quite a subjective classification. We generally deal with things like sparse, intermediate and dense seagrass, and that's on quite a broad range of how that's defined. There's quite a movement now to shifting to underwater automated vehicle technology, and in the past, recently they've been using hyperspectral scanners to identify coral reefs, and it's really just getting a picture of the image using a hyperspectral image profiler or underwater hyperspectral imager, which goes along the sea floor, which is actually similar to this, what we've been designing, either being towed on a sled or mounted onto a boat and actually grabbing the image. Each pixel produces a spectral profile, and that, based on wavelengths reflected back from the object, we're actually able to spectral profile can be produced a unique identifier, very similar to a fingerprint. And this provides an ability to identify algae, plants, and other animals. And as you can see on the side there's just going through the different wavelengths, looking at a coral atoll. And as you move through basically going from Roy G. Biv, red to green to blue, you can see the different aspects of that reef being shown up. The scope of the project, this is actually an international collaboration with Cheng Kung University in Taiwan, National Applied Research Laboratories, SA Water, and also the Airborne Research, I'll get that one correct, Australia University. Excuse me, I was going to blow my nose. The hassles of a cold as well. That sounded quite interesting, everyone. And we're hoping to eventually deploy it over a variety of different platforms, whether using boats or unmanned aerial or underwater vehicles and even aircraft, which is where we're using Flinders University. And as part of the funding was the funding associated with this through the Premier's Research and Industry Fund, which has been trying to access international technology, apply it to a local problem and bring it to South Australia. And then provide opportunities to engage and develop with local industry to develop even further. And part of Lily's work is really looking at actually trying to look at these images. How do you actually process these images that we're acquiring from the hyperspectral scanner? The early trials have been quite successful. We can look at depths, seagrass versus sand, and they're quite clearly distinguishable, as you can see on the images on the side there. Though we're finding that we need further improvements, and that's actually getting some form of spectral library for each of these individual images, for each of the, well, I say for the plants that we're seeing below, and looking at technological or engineering ways of stabilising the UHI, the hyperspectral scanner, on the side of the boat. Part of the work we also did was working with the Flinders University, and we had an honours student, Sam Fullerton, who measured the reflectance of individual species that he collected in the field, and he measured these in the open air, and he found that we actually could identify within a broad range, or close range, in the low 500s and the high 500 nanometer wavelengths, different species, although we had some overlap with Heterosostra and Amphibolus. But we could, by looking at their spectral fingerprint, identify a species, which actually showed some promise. Lily's trying to work on phase 2 and actually deal with some of the issues that we found out in phase 1, that we were dealing with open air, and we didn't have an ideal measurement of the downwelling irradiance as well. And so she's also trying to look at also changes within seagrasses and sand, or location, differences that may occur in water depths, because you might have actually quite dramatic changes in the pigmentation of the plants, and also epiphyte cover, which is posing to be a bit of a challenge for us, because you can have a variety of different epiphytes growing on seagrass, and that will interfere with that spectral image. We've also just got the issue of water. You've got waves and swell magnifying and focusing light as it's going through. You've got things like phytoplankton absorbing light. You've got sediment in the water scattering light. That's before it even hits the seafloor, and then it bounces off the seafloor, and you've got all the same problems again as you're trying to measure it from the top. So in phase 2, developing a spectral library, we took a whole pile of samples that were in the field. We measured downwelling irradiance, and we measured that in natural sunlight, and we actually did it under filtered seawater, just to get an idea of whether that's had some form of influence in a black tank that had no reflectance from it. And at the moment, Lily's comparing the differences between the water depths, so looking at the plants that we collect from different depths, the geographical location, whether that had any influence on the actual spectral qualities, and obviously the epiphytes that are coming in as well, having some form of idea. The preliminary results showed that Heterosostra was vastly different from sand, which thankfully that's good. But really what she's trying to now do is actually see what the differences between the different species as well. And strange enough, sand's not sand, it has its own little problems of what it reflects back with things growing on. And looking at also Landsat 8 data and doing an unsupervised classification, which to my uneducated eyes, I wasn't aware of what it was. It's basically a computer run ahead and actually work out what the different things are based on the image. Then I think Lily's going to say, right, okay, we'll actually put a supervised image in it, or classification, by looking at the spectral library that she has to actually highlight or heighten the ability of the program to identify species. We're also trying to fix the instrument on our boat, rather than having it wander around all over the place, which we had with a sled that was being towed by the boat. We worked with the Juno boys recently towing the sled, and they reckon it was the best thing we could ever have for actually having a jig or a tow, and we're actually hoping a great white would take it, which much to our amusement. Thankfully it didn't happen. We've been in tears. Linking that hyperspectral imagery to the spectral data that Lily's been collecting, and then also looking at the multi-platform approach, and that's really going from the satellite imagery that we can obtain quite easily, looking at some of the imagery that the Flinders University airborne images they can get from their hyperspectral scanner, and then actually proofing it up with the UHI image that we're getting with the underwater spectral scanner that we have for us. So that's basically the essence of the project. Any questions?